Have you ever really stopped to think about how the energy from the sun, which is, 93 million miles away, somehow ends up powering a hawk soaring high above a field? It's this incredible journey that follows one of the most basic rules of life on Earth. So let's jump in and follow that path and see exactly how a star's energy becomes a predator.
So, how does it happen? How does sunlight become a hawk? I mean, on the surface, it sounds almost impossible, right? Pure radiation from a star becoming this living, breathing hunter. Well, to get our heads around this, ecologists use a few key models to map out that flow of energy, and each one peels back another layer of the story.
Okay, so the easiest place to start is with the food chain. Just think of it as a single straight line that traces the path of a meal. And by tracing that meal, you're also tracing the path of energy. It's really the simplest way to visualize who eats whom.
Now, every single food chain, no exceptions, has to kick off with the producer. These are the self-sufficient powerhouses of the ecosystem, things like plants and algae. What they do is they grab the sun's raw energy and through photosynthesis, they turn it into chemical energy, basically food. They are literally the foundation that makes life possible for everyone else.
So, once that energy is all locked up inside a plant, the next link in the chain is the primary consumer. You probably know them as herbivores or plant eaters. These are the animals that come along and eat the producers, and in doing so, they transfer that stored solar energy one step up the ladder. Think of a rabbit munching on clover, or in our example, a grasshopper on a blade of grass.
And from here, well, this is where things get a lot more predatory. Secondary consumers are the ones that eat their herbivores. And then you can even have tertiary consumers who eat those carnivores. These are your predators and your top predators, moving that initial burst of sun energy even further along the line.
And boom, this slide just lays it all out for us step by step. The sun's energy gets captured by the grass. A grasshopper comes along and eats the grass. Then a frog eats that grasshopper. A snake eats the frog. And finally, our hawk, the apex predator, swoops down and eats the snake. You see that path? It's a straight shot, a one-way flow of energy from the sun all the way to the top. Nice and simple.
But as you've probably guessed, nature is rarely that neat and tidy, right? So we need to zoom out from that one single chain and look at the bigger, messier, and honestly much more realistic picture, the food web.
A food chain is a great teaching tool, but a food web, that's what's actually happening out there in the wild. Most animals don't just eat one thing. A hawk might eat a snake, sure, but it's also happy to eat mice or rabbits or squirrels. A food web shows all of these crisscrossing pathways, and it reveals a system that is so much more complex and, frankly, more resilient. And this is the big takeaway from a food web. It's not a line, it's a network. Every living thing is like a node that's connected to many others. You tug on one little thread over here, and the whole thing shakes. So let's actually play this out. Let's imagine that, poof, all the snakes in our ecosystem just vanished. What happens? Well, with a major predator gone, the frog population could just explode. So now you have tons more frogs, and they're eating way more grasshoppers, so the grasshopper numbers could totally plummet. With fewer grasshoppers around, the grass might actually get a break and grow like crazy. And what about our hawk? It just lost a major food source, forcing it to hunt other things more, or maybe even risk starving. It's a total domino effect. Okay, so we've got the pathways of energy down. We know who eats who, but what about the physics of it all? Why are ecosystems structured the way they are? That brings us to our final model, which uncovers a core rule about energy itself. 10%. That's it, just 10%. This single number is one of the most important concepts in all of ecology. It literally dictates the entire structure of life in any ecosystem. So, what on earth does it mean? This is the 10% rule. When a grasshopper eats grass, it only actually gets to use about 10% of the energy stored in that grass. The other 90%? Yeah, that gets used by the grass for its own life, or it's lost as heat when the grasshopper moves, breathes, and just, well, lives. The transfer of energy from one level to the next is incredibly inefficient. And wow, this chart really just makes that inefficiency crystal clear. If the producers at the very bottom represent 100% of the available energy, the primary consumers who eat them only get 10% of that. The secondary consumers, they get just 1%. And those tertiary consumers at the top, like our hawk, they're working with a tiny, tiny fraction, just 0.1% of that original solar energy. And that is why we call it an energy pyramid. The math explains exactly what we see in nature. It's why a forest is filled with countless plants, but way fewer deer and only a very small number of wolves. There just isn't enough energy at the top to support a huge population of apex predators. The shape of the pyramid is a direct result of that 10% rule.
Okay, so we've gone through 3 big ideas. Let's just take a second to put all the pieces together and see how they create the full picture of how energy really flows. So we started with the food chain, right? Our super simple straight line that traces one single path for energy. Then we leveled up to the food web, which showed us the messy, tangled, but much more real way that everything is connected. And finally, the energy pyramid came in and revealed the physical rule that explains why the whole system is structured this way. Because energy is always being lost, life at the top is a rare and precious thing. So we've seen how sunlight becomes a hawk. It's through a chain of consumption, happening inside a huge web of connections, and it's all governed by the strict laws of energy. And that leaves us with one last pretty big question. Knowing how interconnected and fragile this whole system really is, and how limited that energy is that sustains it, what is our role within this web?